Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are five modules. Now we'll be adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept. And if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more. Hello and welcome to class 13 of my series of classes of physics 1. So far we have been talking mainly with the tidbits of quantum theory. It all started with an experiment of 1900, black body radiation explanation by Max Planck. Later on we came to know some more experiments, the photoelectric effect, the Compton effect study. Each experiment was giving you some new insight, some new highlight to all of us. And ultimately, we have developed some two major ideas. One is wave particle duality, that tells us a known wave can be matter-like, light can be photon-like, and the opposite idea, de Broglie hypothesis, a matter can show the property of wave, that is, electron can show the property of waves. Now, we are actually talking about an experiment that could show us, that could highlight us the wave property of the matter. His first question was that the what do you mean by wave nature of a matter, that we tried to illustrate last day. And second question was that if was there any at all any experiment to prove the wavy nature of matter. Answer is that yes, it is there. It was done by Division and Germany in 1927. So two American scientists, they have changed the physics actually. Okay. So how they did it, that journey we started last day. I introduced the basic experimental set of Division-German experiment. Now I have to now talk about the observations of the experiment and what the observation tells you, what leads, what is the new information, the new message you are getting out of it. Okay. So the major objective of this class is to talk about the observations of Division-German experiment and how it proves the wave nature of the matter. And after undergoing this class, you'll be able to understand that is why I am shouting, why de Broglie is shouting that a matter can show a property. These experiments will show you, will tell you that electron can diffract, electron can make interference like normal light. So those things we will see, we will understand, we will observe through this particular class. So now this is me, okay? You can see this is me, okay? And these are all my contacts. You can contact me anytime in my mobile number also. And these are something known to you. Okay, I'll remind you this story, okay, every day, because this is something unique and uncanny, that the basic concepts of waves and matters, and how we divided physics classically and modern physics, how these classical ideas are now getting shattered, because earlier people thought waves and matters are different. Now it's all changing. Courtesy photoelectric effect, it tells that wave can be metal-like. Courtesy Compton effect, it tells us wave can be metal-like, light can be photon-like. Okay. Now we have actually jotted down both the ideas together. Say in general, you say photoelectricity, you say Compton effect, you are dealing with electromagnetic wave. In both experiments, electromagnetic wave is like photons, but there are occasions in nature where it shows the wave nature also, like interference, like reflection, like refraction. Okay. So these together, okay, there was a dilemma that what light actually is. Is it a wave or is it a matter? Answer is that it is both, okay, or it has got a dual character, dual nature. So we talked about the dual nature of electromagnetic radiation or particle duality, and here comes the idea that if a wave can be matter light, okay, the statement of wave particle duality. If a wave can be metal like, obviously the question comes in. You see the same thing, the wave is showing the material property. This has been a wonderful picture that I was showing you. That is how we can say you start with photons, which is the matter, having momentum hv by c. From that thing, I actually express that if photon becomes wavy, it should be wavelength should be lambda is equal to h by p. This idea, whatever I told you, that it generalizes this actually tells us a known matter photon can show wave property. We know light photon is a piece of light, so it has got a wave nature also. That is a normal electromagnetic wave nature. So this practical example is leading to a new type of physics. That is, if a piece of photon, which is a photon, is a piece of light, which is having material aspect like momentum, which collides with electron. Okay, if it has got a wavy part of wavelength lambda is equal to h by p, so any matter might have a wavy part of the same wavelength lambda is equal to h by p. And that is what is told by de Broglie, that a matter can show the property of wave. So this is the basic concept. This is the entire nature. Okay, matter can be wave like or it can be metal like. That is what you are talking about. Now, if a matter is wave like, what is the proof of that experiment? Experiment is that is something you are talking about. This is the hypothesis of de Broglie. He told that any matter can show wave nature. If a matter shows wave nature, then what is the proof of that idea? Okay. Now these are something known to you. We are talking about the wave nature of the matter now. The experiment that was carried out by Davison and Germain. Okay. Davison and Germain did it. Okay, this thing you know, I just move into this. These are all the wavy nature of the matter. Now, I actually told you this issue just to remind you that the wave nature of matter, as we are telling that any matter can show wave nature. If a photon as a matter can show wave nature, that is an electromagnetic wave, normal light. Any matter, as a matter of fact, can show wave nature. But what does it mean? If any matter can show wave nature, what does it mean? What does it mean? What do you mean by wave nature of matter? Okay. The answer I have given with some, these are my classical examples of waves. I actually given very in a funny way, if you could recall. I actually referred to my class. This is me taking a class. So I ask you about a real life example. If I take your class, I move across the board along x-axis maybe. And if I ask you to take a plot, the chance of finding me inside your classroom when I take your class, you see it is all varying. Chance of finding me are all varying while I am standing inside your class. Somewhere you find me more, somewhere you find me less. Okay, but I am there everywhere I go, as you can see in the picture. But as a matter of fact, I cannot be there at all the positions at the same time. So most of the time I may be here. Sometime I may be here. Sometime I may be here. And I never go to this corner, and I never go to the other corner also. So you see, suppose if you take 100 photos of my positions in the classroom, if you scan all those photos, you notice that most of the time I am over this portion of the board. Okay, this portion of the board, that is the left hand side of the board. Because I am a right-hander and I do not take class in Urdu, I told you. So most of the time you will find me there. Sometime I come here. Sometime I come. Here you cannot see me at all. So chance of finding me is varying. Any variation, any fluctuation makes a wave. So you generate a wave of chances of finding me. So this is not me. I told you earlier also. This is not me. This is the my chance or probability, chance is the right term, of finding me. So it's a way of representing me, but that is not me. That is one of my attribute, one of my feature. What feature? What are my probable position when I take your class? Or it's talking about if it is this wave that you can see on the picture on the screen there. That is my wave, but that is not me. That is one of my attribute. This is my matter wave. Okay, and what does it represent? It represents my probable position inside your classroom. So the wave nature of matter is nothing but it's not a physical wave, it's a mathematical wave. It is a probability of wave or chance wave. It is giving the probability of finding an object. Because I am a big matter, I told you, you don't have to take chance to find out me. Okay, you don't have to take chance to find out me. This is my matter wave, as I've told you, but that is not me. Okay, you don't have to take chance to find out me. But for electron, it is moving around. You have to take a chance to find out the electron. Okay, chances will vary, and that variation will make the wave of electron. So the wave we talk about in a quantum mechanics class is nothing but the wave of chances, wave of probabilities. It's not a physical wave. Just like S wave, P wave of quantum mechanics, they are not the usual wave. Okay, they are not light and sound kind of wave. They are actually probability wave. They gives probability of finding the electron in that lobe maybe. Probability of finding the electron in a sphere like that. Okay. So these are all probability waves. They are not electron, just like S wave, D wave, P wave, as you can see. Now here comes the Division-German experiment. Just almost a long recap I told you. This is the experimental setup of Division-German experiment. Electrons are emitted, okay, by heating the filament, by passing through connecting it to a low tension source. So current will pass through the filament. Electrons would be emitted by thermionic emission. Electrons emitted are increasing kinetic energy by passing through a voltage V1. V1 is tunable. Kinetic energy is initial energy of the electron E plus EV1. More V1 means more energy, so you can actually control the electronic energy, and you can increase the kinetic energy of the electron according to your choice. So now there are two plates there. You can see the two green plates are coming in. They actually restrict the electrons to move in any other direction compared to that red arrow which is coming out of that violet box. This violet box I told you the other day also. This is called an electron gun. Okay, because it is producing high kinetic energy beam of electron and highly focused beam of electron. Because these electrons are energized by the help of high tension source, these electrons are focused by these two plates. These electrons are incident on a nickel crystal, and after incidence it will be scattered in all possible directions. We have considered few directions, and if it is scattered in some angle, say phi, it will be collected by a collector. Collector is connected with the negative potential and also an ammeter. Now that the negative potential or retarding potential Vt will not allow all the electrons to enter inside the collector. It has got a fixed value. Only those electrons which can overcome the Coulombic repulsion due to Vt, they will be collected by the collector, and you can see a current there. Okay, in the output. Okay, so basically for a given position of the collector, say phi, now you can measure current. So experimentally also, say now suppose the position is phi 1, you measure the current as phi 2, we measure the current as I2. Phi 3, measure the current as I3. So you get a table. What was done in the experiment? Accelerating voltage is a 40 volt. Vt is fixed. So Vt fixed means which electrons are allowed to enter, which are not allowed to enter inside the collector, that you know. Okay, now V1 is equal to 40 volt. Okay, accelerating voltage. So what would happen under this circuit condition? I am changing the position of the collector. So that means I am varying phi. For each phi, I am getting the corresponding current. Okay, and suppose same thing was done with some more higher voltages also, 44, 48, 54, 60, 68. So basically more voltage means you provide more kinetic energy to the electron. So it is expected more of them will be collected by the collector and will be getting more current. So let us see what the observation is. This is the observation. You see, if you look at the graphs, you notice at the lowest value, say at 44 volt, you can see this graph has got a small kink there. Okay, you can see there. If you look at the graph at 44 volt, Okay, there is a small growth here, this one. There is a small spar here. There is some extra current. So that means small spar indicates, actually one experiment was more done actually. At 40 volt also one reading was taken. At 40 volt, the graph often was almost like a smooth graph. The idea is that this is at V1 equal to 40 volt. The idea is that you see it's all polar plot. So any point here, if you define with any coordinate system here, so this length vector is going to give you the value of the current R for that particular position. Suppose this is phi 1. If you bring it here, obviously this angle is going to change. Suppose this angle is say phi 2. And this will be your corresponding current. Okay, current will also vary. Okay, current will also change. If it was I1, this will be some other current, say I2. So idea is that any point here on this curve represents two things. The length means current, and this angle is actually the position of the collector with respect, and the angle between the collector and the scattered beam and the electron beam coming in. Okay, this angle. You can see this picture. This angle. This is the angle. That is the direction of the scattered beam and the electron coming in. This angle. So now, any point here, what you notice? At 40 volt, it becomes a smooth graph. At 44 volt, there is a small spark. So that means, in certain direction, you are getting more current. Suppose now at 48 volt, you see it is more. At 54 volt, you see it suddenly it goes up. You see, to give a better understanding, I come to this picture. If you look at all the graphs, you see these are the graphs obtained at variety of voltages. At 40 volt, so what does it mean? At 40 volt, V1 equal to 40 volt. These are all the values of V1. If I choose any point here, this point, this is R, the current. And that is the angle. This angle is phi. What you notice at 44 volt, in certain direction, you are getting bit of extra current in this direction. And what you notice from 44 to 48 volt, what you see, in that particular direction, you keep on getting extra current. Question is that why? Why you should get more current only in certain direction? The point is that if you look at the arrangement of the Davison-German experiment, you see electron beams are coming in. Okay, they will be accepted by the collector and will give me some current, maybe I3 or whatever it may be. Now, whether these electrons should be collected by the collector or not, this depends on the initial acceleration. And I told you this, you can always vary this V1, you can change this V1. Say at 40 volt, our experience was that it was a smooth graph. Now at 44 volt to 48 volt, what you notice is this much. So I'm increasing the voltage, this V1 I am varying from 40 to 44 to 48. So that means by theory, I am actually increasing this term. So that means by default, I am increasing the kinetic energy of the electron. So that means I am making more and more enable for the electrons to be, they are more energetic, they are more enable. Okay, so to be collected by the collector. That means in this way you are actually doing. Okay, so now it is expected if I increase the voltage from 40 to 44 to 48, so basically I am increasing the electron kinetic energy. I'm keeping on increasing this electron kinetic energy. So more energy means it is expected more and more photons, uh, more and more electrons will be accepted by the collector, and this current is expected to grow up. I should get more and more current. But in the so suppose you begin at 40 volt, go to 44, 48, etc. So what you are doing, you are increasing this kinetic energy term of the electron. You are increasing their kinetic energy. Okay, you are increasing their kinetic energy. So what it does is actually, uh, you see, it is incident, it is being scattered, and I am trying to accelerate them. Okay, I am increasing V1, and I am keeping it at variety of voltages. And what you notice that is interesting. The observation is that as you go from 44 to 48 to 54 like that volt, in only one position of the collector, you are getting more current. Question is that why? Because this is an observation of the experiment you are doing. You see, at 40 volt, okay, at 40 volt it was smooth graph. At 44 in one direction more current. 48 volt more voltage means you are getting more direction current in that particular direction. Okay. So basically, the matter is that you are expecting that more voltage means electrons are accelerated more. They are more energetic. More of them will be accepted by the collector. I will get more current. I am getting more current. But my question is that why should I get it only for one particular direction? Okay, that is a very important question. Okay, why? Why it in that is for theta equal to 50 degree? Why it is happening here? In this particular direction, yes. Why you are getting more current only for one specific direction? Ideally, when you increase the voltage, all electrons are excited, all electrons are energetic. So all of them should be collected by the collector, and I should get a lot of current. But here you are getting only partial current, that is the current due to the due to the four voltages, okay, 40, 44, 40, 50, 48, 54, 60, 68, like that, okay. Interestingly, what you notice, more voltage means you are getting more current, that is expected, but that is only for one specific direction, that is V1 equal to 40 volt, or for only one specific purpose. If you increase the voltage further, so that means you are making the electrons more energetic theoretically. So you are expecting to get, you will get a more current, but it is not happening. Actual peak has come at 54 volt. 54 volts. So what you notice is the and theta is equal to 50 degree, as you can see there. So all the electron beams scattered in the direction are making constructive interference. And what is happening? What you notice here, you are increasing the voltage from V1 to 40 to 54. So electrons are more energetic. So more current I'll get. I'm getting more current. No problem with that. Okay, problem is that I'm getting it only for one specific direction. In that case, it's like theta equal to 50 degree. Now, another bad news is that if you cross 54 volts, suppose you get to 60 or 64 or 60, what you are doing, you see, is this much. Say, why it is dropping down? Because if you start from 40 to 44 to 40, you may say more voltage means more energy for the electron, and I will get more current. But that is not working well here, because you see, beyond 54 volt, you see, you are getting more current in a particular direction. Okay, that is okay, but not that huge current that you see because of at 54 volt and theta equal to 50 degree. It is growing, but not a radical growth. Okay, understand? But it is growing. It was huge increase in the intensity was observed. Okay, in fact. If you now analyze all the other figures, what you notice, Beyond 54 volt, it's bad news. Okay, at 60 volt, you can see the peak is diminishing. At 64 volt and okay, at 68 volt also they continue. But what you know, what they notice that more voltages means okay, more acceleration, more chance of electron being accepted by the collector. I will get more current. But that is under question now. But okay, question is that how do I get more current? I will get more current, but how do I justify that I am only getting for one specific position of the collector, that is theta equal to 50 degrees? Why it is happening? Another important issue is that you see below above 54 volt, the 60 volt or 68 volt, you see spar is almost gone at 68 volt. So that means from 60 volt to above 68 volt, there must be something is happening. Or in other words, what you have been noticing, that more voltage means more acceleration, and so you'll be getting more current because more electrons should be collected. That is not always true. That is partially true. Only for one specific direction you are getting it. And it is not working beyond at 54 volt also. It is going up, fine. But you see only at theta equal to 50 degrees, okay. And what he could not, or scientists could not explain at that point of time, that if, okay, fine, it is growing up and it has gone rapidly at theta equal to 50 degree, applied voltage equal to 54 volt. But why it should drop from there on? Okay, what you notice, you see above 54 volt, that is from 60, 64, 68. What you notice, current is again, it has dropped down, diminished, almost a smooth graph is there, 68 volt. Why it is falling down? So that means the way we are looking into the situation, that electrons are coming, electrons are collected, that will give me the current. Okay. But we have been looking at the whole situation in that way. I will be controlling the accelerating voltage. For each accelerating voltage, I will be removing the collector. I will be noting down the point and we will be plotting it. That is the process. Now, after plotting, there would many open questions will come the moment you look at the graph itself. Okay. Uh, that is the peculiarity at 54 volt. Huge current, huge abrupt current you are getting. Okay. Why you are getting so much of current? Division and German try to explain this by making two assumptions. First assumption, you understand they thought about the wavy nature of the matter, in this case matter electron. And the current that you notice there, according to them, is a measurement of intensity of electron wave. Okay. Now this idea is absolutely unique again. I'm talking about electron wave intensity is given by current. Why? To make you understand this, so I hope you understand the two assumption. Assumption one is, as expected, we are talking about the wave nature of the matter electron. And the second point is more critical. The current is the measurement of intensity of electron. Why? How do I say this? Because of this. You see, I've got so many bulbs there. Intensity 2 is glowing, intensity 3 is glowing heavily, and there is intensity 1. The bulb is with intensity I1. Okay, it has taken a bit of time, okay, in getting into this full phase. So what you notice there, that all three bulbs are glowing. Okay, all the three bulbs are glowing at various intensity, obviously 1, 2, 3, etc. So now try to realize suppose the intensity, the bulb with intensity 3, it emits it's a lot of light there. If it is emitting a lot of light, I will say it is emitting a lot of photons. Okay. It will emit a lot of photons the moment. Okay. Okay, a lot of photons are coming out. So you may say if, and you can see, realize by three intensities are presented on the screen. Obviously, third one is the most intense. So that means if intensity is high, it is emitting more radiation. Okay. More radiation it is observed there. Okay. So more light means more photons coming out, and more photons means you see more light coming out. Whatever you see. If more light coming out, you can see the three bulbs glowing. Obviously, the most intense is the right hand side one. Most intensity means, or high intensity means, say high large photons are a large number of lights are coming. So large lights are coming means large number of photons are coming. Okay, that is a concept. So more photons means more intense the ordinary light. Okay, so now this gives you a little signal that in more photon means more uh, intense the ordinary wave. Similarly, for electrons, if you try to see, for electrons you try to see like this much. Just a second. This is the explanation. Okay, the more photon means you can see there. In the bulb you can see it is glowing more. So more intensity is coming. You see, more light means I say more intense the ordinary light. So that means it is emitting more photon. Right hand side you see more intensity the electrons. What I am telling. Similarly, more photon means more intense the ordinary light. Similarly, more electrons means more intense the electron wave. Same logic. If you consider light as a wave and photon as a matter, so more matter photon emitting more means more intense ordinary light. Similarly, if matter electron moves, if you consider wave nature of the electron, so more intense the electron wave. And if more more electrons are there, and if I calculate the corresponding current, it will be more. If more photons are coming, more intense the electron wave, more intense the ordinary source. Similarly, if more electrons are passing, so more intense the electron wave. Okay. So basically, that's why we say, and how do you measure if more electrons are passing? How do you realize that? Through the ammeter reading. So that is what you have been doing in the experiment. So this basically, you can try to realize it, is that the current we measure with ammeter. So that is giving me the measurement of the current. But more current means more intense ordinary light. Okay. More electron wave, because more current means more electrons are passing through. So the logic is that more photon means more intense ordinary light. Similarly, more electrons means more intense the electron wave. If more electron passes, obviously you'll get a current there. As you can see there, at 54 volt, there is a peak coming in. So obviously now you have to explain why it is often this type of peak. Okay, why it is often this type of peak. Okay, at theta is equal to V1 is equal to 54 volt, the applied voltage. Okay, you can say at peak theta is equal to 50 degree passing through a peak. Okay, so these peaks are all explained by this idea that there must be that current that is passing through. Okay, it is becoming extremely high. So more current means more electrons are passing, and I will get a more electrons are passing means I will get a lot of current there. Okay, so very simple. Just to realize it. Okay. Now this you can, if you compare the picture, you can see there is a huge growth in the observed. You can see there is a huge growth. Is a current observed by the meter there. A radical growth in the current observed. Okay. There is a huge growth, radical growth that you can see there. Okay. Now, question is that current there, that huge growth is taking place. Okay, fine. But at the end of the day, there is a measurement of current. And current, as I mentioned, is the intensity of electron wave. So what you notice, there is a huge increase in intensity of electron wave. And we know in nature, intensity can reduce or intensity can decrease because of one optical phenomena. The name of the phenomena is in, interference. Okay, if constructive interference is there, intensity will grow, and if destructive interference is there, intensity will drop. But the message is clear. The problem we have been facing, we are trying to represent the or establishment of the nature of the matter. We are there in the detailed discussion. As you can see, this wave is a wave of chances. Okay, and the main problem, as you can see, is that 54 volt and theta equal to 50 degree, and obviously, okay, the observation is this, that all the electron ions are now scattered in the direction theta equal to 50 degree. Okay, and they are making, what is their idea? Electrons are making interference. Okay, they are making constructive interference. Okay, so we get a theory now from division and Jana that electrons are heavy. Second point is if electrons are heavy, then if it shows wave nature, that will be manifested by some deep wavelength. Okay, and what you notice now? Now I am telling now you use that idea. Okay, and to find out the uh, wavelength of the electron beam, because whatever I told you, that it is an idea, it is whatever I told you, this is our conception, is that in that experiment, say, um, what you notice, there is an abrupt growth in intensity. Okay, now why that abrupt growth in intensity is taking place, and it is happening very regularly. I have shown you just now at 44 volt, at 48 volt, current is slowly going up. Okay, because common sense, because you are increasing the applied voltage. Okay, current is going up because you are increasing the applied voltage. Okay, kinetic energy increases. Now the point is that, as I mentioned, current is a measurement of intensity. So that this huge increase in intensity, as you know now, uh, is happening because in nature, intensity can decrease or increase because of only one phenomenon, that is interference. So as if some constructive interference of electron beams are taking place, and because of constructive interference, you get this peak, etc. So all the electron beams are scattered, okay, and making a constructive interference. Now this is a theory of division and Jama. Now obviously you have to now justify the theory. So how do you justify? You can do the justification. If I do the justification, if I measure, do something realistic. So what shall I do now? I will measure the wavelength of the electron beam. Okay, using this theory that electrons are waves and making an constructive interference. And I will also compare that with the experimental data. And if there is agreement with each other, this observation, whatever we have said in this theory of division and gamma, they will prove to be right. Okay, so let us do that. Okay, if see any solid is like this much, so let me do that small calculation. Okay? Directly. Experiment arrangement is like this much. So this is a filament connected with low tension battery. Electrons will come out of the electron gun. Okay, just let me use a better pen. This is the electron gun. Okay, they are accelerated by the high tension battery. We apply a variable voltage V1 like this. Now this is incident on the nickel crystal. Okay, this is the crystal. From there on it is scattered, collected by the collector, and here I expect to get a reading. Okay, and this is the angle of scattering phi according to my description. Now basically in front of you I will now show you. My objective is to measure I will now measure this wavelength of this electron beam using the theory. What is my theory of Davisson and Jarma? There is electrons are like wavy. Electrons are showing wavy nature in the experiment. That is my theory. Electrons are showing the features of waves, wavelength lambda, and all the electron waves scattered in the direction theta equal to 50 degree or phi equal to 50 degree are making constructive interference. Because of this constructive interference, you see this abrupt growth in the current. Okay, this is the current value. There is constructive interference, and theta was measured at 50 degree. Now to explain this, so the idea was that electrons are making interference. So what they will do, we will now try to utilize this idea of constructive interference to measure the wavelength of electron beam. If we try to measure the wavelength of electron beam, it would be like this much. Okay. Now this nickel is an excessive crystal. Okay. Any crystal, as a matter of fact, you see surface on which electron beam is incident is like this. The electron beam is actually falling on this surface. Now this face is actually crystallographic plane, one face of the nickel crystal. So basically I have to show you. You see, this is the face upon which it is falling in. It is, okay. So how it is happening, it is, let me show you. So any solid is made by periodic arrangement of atoms. And in a solid, there are certain planes which are at some angle with the top surface. These are those planes. What is happening? Electron beam is coming in. This is the electron beam coming in. So wavelength lambda. So it should have velocity v1 equal to mu lambda. Now it will now enter inside the nickel crystal because this line is the top surface of the or 111 phase of the FCC nickel crystal. Now it will enter. Now you see there is a change of medium taking place. Earlier it was in air, now it is inside the crystal. So the wavelength will change to lambda prime, and let this corresponding velocity be v2 equal to mu lambda prime. So now we can define refractive index, that is reflect outside by inside. Okay, lambda by lambda prime. Now here it is incident on one of the electron. From there on it will be scattered. So it is lambda. Now from here on it will go out. Okay, and this angle actually we see out in the experiment. So for example, In the particular case of that constructive interference we are trying to explain, phi is like 50 degrees. Okay, now this phenomena that is taking place here is very similar to X-ray diffraction in Bragg's law that you also studied in X-ray courses. You'll be learning it. So these are the periodic arrangement of atoms. Here, electron being scattered from atomic plane. Here also, X-rays are scattered from atomic plane. So if this is incident angle at angle theta, suppose this is another beam of X-ray. It is also incident in the same angle theta. So ultimately, this X-ray beam will be scattered from here. Now, what is the constructive interference of this X-ray beam? That is given there. Okay, that is if the separation between the scattering plane is say d, then the condition of constructive interference is given by 2d sin theta in lambda prime. Okay, considering lambda is in lambda. Okay, lambda is the wavelength of X-ray. Now, this idea will be utilized in this also. Okay, because here also, here X-rays are scattered, here electron beams are scattered. Here, suppose this is the other beam coming in. Okay, it will come from there on, it will be scattered. Okay, from here on, it will go out, and ultimately these beams will interfere. Constructive interference is there. Okay, interference will take place. Understand? So they will now interfere constructively. So that is a theory. So now let me measure the wavelength. I will utilize this Bragg's idea. Let's see. There are two conditions of Bragg's law. First is that of this constructive interference is that these angle of incidence and angle of scattering both should be same. If these two are same, by the geometry of the problem, we can understand this is normal here. If this is say theta 1, this is also theta 1 because that is 90 minus of that. That is according to normal reflection, these are angle of incidence and angle of reflection. So two conditions are there. One is this condition, another is that this is almost like a reflection kind of thing. There is angle of incidence, this is also theta, and the angle of scattering are same. So these two ideas, just like here X-rays get scattered, like makes constructive interference, we will utilize there also. Where electron beams are coming in and making constructive interference. Okay. So now we'll try to explain this. So this is a picture. So this is your electron wave or wavelength lambda coming in, velocity mu lambda, and inside the medium it is changing to this much. From here on it is getting scattered. Here the velocity v2 lambda prime, refractive index we define as this much, v1 by v2. So mu the refractive index equal to lambda by lambda prime. So now I told you just about Bragg's law a few minutes back. If I consider another beam of electrons here, so it will come down. Same thing will happen to this also. So this will be scattered from here. So ultimately these are atomic planes. So this is a scattered beam. It will be going out from this by some angle. Maybe phi is equal to 50 degrees. Now they will interfere constructively. So now we consider what happens in Bragg's law. That is also true. If this angle, if I draw a normal here, Now suppose this angle is, say, for example, we consider this here theta prime. So by Bragg's law, this is also theta prime because these two angles are equal. Okay. So now if this is theta prime, this is theta prime, you can understand by geometry of the problem, this is actually 2 theta prime. So now we can define another refractive index that is equal to sine phi by sine 2 theta prime. So from here on we can write down lambda prime sine phi by sine 2 theta prime. So what is sine phi? Now to proceed further, I have to get an expression of lambda prime because I want to get the value of lambda, the wavelength of electron. What is its value? Now what shall I do now? I'll now ask you to get lambda prime. You again use the other Bragg's law, that is 2D. Use Bragg's law. If I use Bragg's law, it is 2D. D means separation between these planes. Sine of the angle, you see, in original Bragg's law, this is the original Bragg's law. This was the condition of constructive interference. If this is theta, this is theta, this angle was considered. When you write down 2D sine theta is equal to n lambda prime, for example. So now, so that means here the theta is chosen with the horizontal. So basically now in my drawing, theta primes are not with horizontal. So you have to consider these angles, okay? The angle with the horizontal like this. You see, this is the X-ray coming in. It is getting scattered. This is the 90 degree. This is theta prime. So this angle is 90 minus theta prime, nothing but. And by geometry of the problem, this will also be 90 minus theta prime. So when you write down this formula, if you have to use Bragg's law, okay, so obviously this you have to consider this angle with the horizontal. So this is sine of to the sine theta is equal to lambda. Lambda, suppose, is the wavelength of the beam coming in, okay. Here it will be lambda prime because you see it is being scattered from this planes. Just like here X-rays are scattered, here electron beams are being scattered. So this will be 2D cos theta prime in lambda prime. For first order, n will be equal to 1. Now if I look at this expression, this gives me lambda. Lambda prime is how much? For first order expression, it is actually 2D cos theta prime sine phi by sine 2 theta prime means 2 sine theta prime cos theta prime. Now cos theta prime will cancel, 2 will cancel. Wavelength will be D sine theta prime sine phi. Okay. Now in the experiment, this quantity is measured as 2.15 angstrom. It can be calculated from Miller indices. And as you can see in the experiment, this phi is basically 50 degree, the angle made outside. So the expression of lambda is therefore like this much. Lambda is like 2.15 angstrom and a sine 50 degree. If you put it, it is like 1.67 angstrom. Okay, so this is the theoretically estimated value. Theoretically estimated value is therefore 1.67 angstrom, as you can see there. okay, lambda of the electron. Now it was compared with the experimental measured data directly. There is no other experiment done before this, so you should realize it has to be verified from the same experiment. That therefore this is the experiment of division of gamma. Electron beams coming out. This wavelength is measured as 1.67 angstroms here. It is being scattered by some angle say phi, collected by the collector, and on so on. Okay, put it down the current and etc. etc. So these voltage. Okay. Now what was happening? This was a filament. This was a low tension battery, and to accelerate the electrons, I connected with a high tension battery also. The idea is that if I apply a voltage V1 here, so it will be energized. I can control this voltage. I told you. Now, just now, by the theory of that electron beams are like waves, and they are showing the wave nature. So this is scattering of electron waves. They are making interference and giving this huge growth in the current. So these are the entire observation is by us only. Okay, you can see there's a huge growth in the current or abrupt rise in the intensity. So why it is happening? We have explained that due to constructive interference of electron wave. And with that theory, this lambda is measured at 2.68 angstrom. Now this can be verified from the same experiment by the idea of that one. Okay, that is what is the Broglie formula is by E. What is momentum? Momentum is basically half of m square, okay, or h by mass into velocity into v. What is u? Mu. U is basically root over 2 ev by m. What is mu? Root over 2 mv. So basically, lambda from this expression is h 6.62 10 to the power minus 34. So root of mu is root over twice m. Okay. How much, which m it is? Electron mass. Okay. M EV 1.60 to 10 to the power minus 19, and applied voltage is basically it happened everything is at 54 volt. Okay. So this is your wavelength. If you put all the values, the lambda is like 1.61 angstrom. So this is the experimentally measured value. So you can see here, this theoretical value is 1.67 angstrom. What is the theory? Electrons are like waves and making constructive interference. And experimental value is close to 1.61 angstrom. So you can see there is an agreement up to first order decimal. Okay, there is an agreement up to first order decimal. So obviously, the idea that electrons are like wavy and making interference, okay, that is shared. Okay, so that is now shared. So now, with this in mind, if these are the calculations I've just done now. This is just now I told you. Use these Bragg's law to a good effect, and these electrons are like waves. Okay. So basically, what does it prove? It proves that the wave nature of the matter is a reality, as is thought by division of Jama. If one person becomes very happy because of that, it's nothing but Louis de Broglie, because ultimately everything came up from his idea. Okay. So with this, we conclude, at least we can realize, at least we can see the experimental calculated value is like 1.67, and theoretical value is more. So basically, the idea is this: we have made enough calculation to show you that wave nature of the matter is not a story; it is possible. Okay, it is detectable. Okay, it is measurable. Okay, and you can see here that corresponding wavelength also is measured, and the theoretical value and experimental value are almost they're corrected to first order and decimal. But after that, I tried to tell you the experimental arrangement, observation, what is the major observation, same thing, that it is the way it's manifesting the wave nature of the matter. Okay, so here we conclude today because we've got a long way to go. Okay, after this, okay, we'll move into the another type of discussion. Okay, thank you.
You and me were meant to be in the great outdoors, forever free. You and me meant to be in the great outdoors, forever free. Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together, it's so beautiful. You and me, we meant to be in the great outdoors, forever free. Sometimes you need to go and take a step back